Hello and welcome to this video on what is voltage as part of our series on electricity. My name's Eleanor Wiley and I'm a coach with the Institute of Physics. The concept of voltage, or to give it its more useful and descriptive term, potential difference, is widely misunderstood. Personally, the misconception that a battery or a cell gave electrons energy rather than just exerted a force on them caused me cognitive conflict for decades. In order to understand the concepts here, it's good for students to have met atomic structure and to have done some electrostatics, because in this video we're bridging between a static electricity, where charged objects exert forces, and current electricity, where electrons move through wires. I think it's useful to spend some time with your students bridging between these concepts and explaining why electrons actually move. Be explicit with your students that current electricity is so important to us because moving electrons can do work, just as moving water can do work in a water wheel, or moving steam can do work. Moving electrons can drive a motor, they can have a heating effect in an element, they can work a computer. There are so many things that we use moving electrons for every day. So we're now going to explore this concept of electrical working. It's useful to remind students that work is done when a force moves something over a distance. It's a measure of energy shifted. And we need to do work to charge things. This is because positive and negative charges attract one another. So we're taking a neutral atom and pulling away the negative electrons from the positive ions. So if we've got two charges here, one positive and one negative, they're attracting one another. And we need to do work to pull them apart. We need to exert a force. However, when objects have the same charge, they're repelling one another. So in this case, the opposite is true. We need to do work to bring them closer together. If we need to do work to move a charge from one point to another, the points are at different potentials. The Earth is always taken as zero potential. The potential of a point is the amount of work that must be done to move 1 coulomb of charge to that point. And the unit of potential is the volt. So if we look at a couple of examples here, we have 1 coulomb of charge that is at the Earth voltage of 0. If we wanted to move that to a point that has a potential of 1 volt, we would need to do 1 joule of work to move it there. In this example, we've got our same coulomb of charge, but this time the point we're moving it to is at a potential of 1,000 volts. So in this case, we need to do 1,000 joules of work to move it there. Objects can have negative charges too. So here we've got our Earth again and our 1 coulomb of charge by a negatively charged body. So this time we need to do work to move the charge away. So to raise it up to the Earth, we need to do work. So we say that body is at a negative potential. If we have two insulated charged conductors, both at 10,000 volts, they are at the same potential. So if I connected a voltmeter between them, it would read 0. And if I was to connect a wire between them, no electrons would flow because there is no net force, as there is no potential difference. However, if I was to have one charged conductor again at 10,000 volts, and this time the other is at 2,000 volts, this time, if I connected a voltmeter between them, it would read 8,000 volts because there is a potential difference of 8,000 volts. If I connect a wire between them, electrons will flow from the one on the right to the one on the left. So even though the one on the right at 2,000 volts is positive, because it is at a lower potential than the one on the right at 10,000 volts, electrons that are already in the wire will be attracted towards the one on the right. So in terms of electron flow, electrons always flow from a point at low potential to one at high potential. Now we're going to look at some models that you could use in your classroom to help convey these ideas. This model can help students understand that it's a difference in charge or potential that forces electrons to move. If I was doing this with a class, I would have students holding up mini whiteboards with charges drawn on them, and I'd have one person as an electron who could move. If I have an electron and no charge either side, there is no force acting on that electron. If I was to change one of the no charges to a positive charge, there would now be a force of attraction between that electron and that positive charge, like this. If I was to change the positive charge for a negative charge, the force would now be repulsion, so the force acting on the electron would be to the right. If I was to have a negative charge on both sides, there would still be the repulsion from this charge, but there would also be repulsion from this charge. So I've now got forces acting in opposite directions which cancel each other out, leaving no net force. Similarly, if I had a positive charge on each side, there would be a force of attraction from the charge on the left to the left, and a force of attraction from the charge on the right to the right. Again, these forces will cancel, leaving no net force. If I was to increase the number of charges on the left, so I've now got one more charge on the left than the right, I would still have a force of attraction to the right, but now I would also have double the force of attraction to the left. So in this case, there is a net force acting to the left like this. I would now have two more positive charges on this side than this, so I would have double the net force. And if I was to add yet another charge, I would now have three more charges on this side than this side, so I would need an arrow 3 times as long to represent a force 3 times the size. It's the same with negative charges. If I was to have 2 negative charges on the left and 1 on the right, I would have a force of repulsion acting to the left from the charge on the right, but double the force of the repulsion acting to the right from the charges on the left. So it's not what charges we have, but the difference between them that's important. If I was to have a positive charge on the left and a negative charge on the right, I would have attraction to the left and repulsion from the right. So my arrow would be twice the length. The bigger the difference in charge, the bigger the forces. So if I was to have 4 positive charges on the left and 4 negative charges on the right, I would now have an attraction of 4 to the left, but also a repulsion of 4 to the right. So I would need an arrow 8 times the length of my single one. This is what happens in a battery. One terminal has a negative charge and the other has an equal and opposite positive charge. As a wire connects one terminal to the other in a circuit, and there are electrons in that wire. So the electrons in the wire are being repelled from the negative terminal and attracted to the positive terminal, and it's that force on the electrons that causes them to move around the circuit.
This model can show that difference causes change. It's just 2 mixing bowls with one end of a string of Christmas tree beads attached to each. You can use this model in several different areas of physics, looking at pressure difference or temperature difference. But in this case, we're looking at potential difference. So potential is represented by the height at which I hold each of the bowls. And the current is represented by the flow of beads between the bowls. So, to begin with, I'm holding the bowls at the same height. There's no height difference, meaning no potential difference. and there's no flow of beads between the two, so no current. If I raise one of the bowls a bit, I'm now representing a potential difference, and you see the beads are flowing from one bowl to another, representing a current. If I show a greater height difference, that's going to represent a higher potential difference, and you'll see the beads move more quickly, representing a greater current. So it's not the potential that each part of our circuit is at that's important, but the difference between the two. That potential difference is what we measure with a voltmeter.
When I drop a marble onto this windmill, it does a bit of work. It forces the blades on the windmill round. If I drop it from a greater height, it does a bit more work. The marble hits the blades with more force, so we get more movement than we do at a lower height. In a circuit, charge can do work too, not because of a difference in height, but because of a difference in potential from either end of the battery. The greater the potential difference, the greater the force the charge can exert on the components in a circuit, and the more work can be done. So the work that can be done by the charges in a circuit depends on the potential difference or voltage of the power supply. We need a source of potential difference in order to get our electrons to move and do work for us. In cells and batteries, it's a chemical reaction that separates the charges, producing a potential difference. Here we have a very simple circuit with a cell joined to a bulb. Because there's a potential difference, electrons in the wires connecting the bulb and the cell will move. And hopefully you'll remember they'll move from the end at low potential to that at high potential. So this is the direction of electron flow. Unfortunately, people knew that charges moved before they knew about electrons. So when they first started talking about electrical current as a flow of charge, they talked about positive charges. Even when they knew about electrons, this didn't change. So we still talk about conventional current flowing from positive to negative, even though in reality it's the electrons moving in the opposite direction. So we have this historical anomaly that's caused problems for physicists ever since. So to summarise, moving electrons can do useful work. We need a potential difference for electrons to move. A potential difference means that forces act on electrons, pushing and pulling them through components. The greater the potential difference, the more work electrons can do. And cells and batteries exert forces on electrons. In England, we talk about conventional current flowing positive to negative, but really electrons move in the opposite direction. Thank you for watching this video. I hope it's been useful in thinking about how to introduce potential difference to your students. Please watch the other videos in the series, and do look at Talk Physics/events to sign up to one of our live electricity CPD sessions. Goodbye.